Okay, so in this video, we're going to look at the circuitry laws revision task that I gave you, so we can highlight any areas that we need to work on. So let's start off with question one, a nice simple one, looking at how current works in a series circuit. And I don't really need to go into too much detail here. You should know that wherever you measure current in so this is ammeter 1, ammeter 2, ammeter 3. Wherever you measure the current in a series circuit, you should measure the same value all the time. So A3, A2, and A1 will all be the same. Okay, so let's move on to the ones where people start going astray. And I'll get this up on OneNote so I can annotate it. Okay, so what we're trying to do is put these currents, A1, A2, A3, in rank order and describe a law that they will be following. Okay, so first of all, we can identify which one the biggest will be. This one, this one here. So the current through the cell must be the biggest. Must. And quite a few people didn't have that one, but if you think about it, the current is coming through your cell here, and then it will split. Some of it will go here, some of it will go here. So A1 is going to have to be the biggest one. So we can already put them the first one in our ranking system. We know which one has to be the biggest. And then what we have to do, I'll change color because we're looking at different things. We then have to look at the resistances in the two sections, because a bigger resistor would mean you get a smaller current. So essentially what we're going to see is, so we're going to see more charged particles per second through smaller resistor. Okay, so that allows us to then put the A3 and A2 in order. So we'd expect to see A3 and then A2 being the smallest one at the end. In terms of a law that they follow, we should find that A1 is going to be equal to A2 plus A3, because we're not losing any charged particles anywhere. So, let's say 10 charged particles per second are going through A1, and then we might have 6 going through A3. That would mean that 4 had to be going through A2. So we're not losing or gaining any charged particles. That's why we're following this law that you can see here. Okay, so that's those are our two current laws. In series, current's the same throughout the circuit. In parallel, the two currents will add together to give you the current going through your power supply there. Okay, so that's our current laws. Let's have a look at potential difference initially in series. So here, what we're looking to do is identify which one will be bigger, V1 or V2. So the key here again is looking at the two resistances, because that's important. So potential difference works the opposite way to how current works. So we said in the on the previous question that a bigger resistor will get a smaller current going through it. It's exactly the opposite for potential difference, because the way I want you to think about the resistance is its potential difference to get a current of 1 amp. That's how I think about what resistance is. So if you have a bigger resistor, you have to have a much bigger potential difference to get the current of 1 amp here. So what we're going to see is that V1 is going to be bigger than V2 because the resistance is bigger. So you have to remember that the laws work a bit differently with current and potential difference. So here, bigger resistance means a bigger potential difference when we've got series resistors like this. Okay, so if we then have a look at our potential difference parallel, here, the way this works is that V1 must be equal to V2, because if you measure the potential difference across parallel components, you always measure the same value. And in this particular circuit, that's actually going to be equal to 4 volts, because there's no other components in series or anything. So if we draw a loop around here, the total EMF we've got is 4 volts. Therefore, the total potential difference around this loop must be 4 volts as well. So V1 must be equal to 4. We could equally draw a loop around our circuit that looks like this. And any loop we draw, the EMFs must be equal to the potential differences. So again, in this loop, the EMFs is 4 volts. That's our only power supply. Therefore, V2 must be 4 volts as well. So essentially, any energy we're putting into a charge is also being taken away. Okay, so that's what we should find with this circuit. Let's now have a look at incorporating our calculations and resistance and things like that. So in this, so we're looking to fill in the gaps here. So in this circuit, the total resistance is, well, remember for series, you know that the total resistance is just the sum of the resistors. So in here, all I'm going to have to do is put in 15 because it's 10 plus 5, and 15 is a two significant figure number, so that's all fine. Okay, and this means that the current through the cell is, so we know that resistance is potential difference divided by current, which means that current is going to be potential difference divided by resistance. So the total potential difference applied is 4. The total resistance we've just seen is 15. And if we do 4 divided by 15, I'm going to need to grab my calculator. Okay, I probably should have thought of that before I started making this video, but never mind. Okay, so 4 divided by 15 gives, so the number comes out as a infinite, like, recurring number. So it's like 66666, blah, 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 blah. And that's measured in amps, of course. But if you see here, it tells you it wants the answer to two significant figures. So we're going to write that as 0.27, because obviously the 6 makes the 6 round up to 7. So the potential difference across the 10 ohm resistor can be calculated to be, well, another rearrangement of that same equation that we've been using would be V equals IR. We know the current is 0.266, blah, blah, blah. Resistance is 10. And if we do that calculation, we're going to come out with 2.666, blah, blah, blah. Again, we want our answer to two significant figures. So I'm just going to write 2.7 volts in there. And therefore, the potential difference across the 5 ohm resistor, well, we can just use our EMFs is equal to potential differences rule. So V2 is going to be equal to 4 minus 2.66, blah, blah, blah. So let's do that calculation. It's going to be like 1.33333. So that's going to be 1.333, blah, 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 volts. So then that's just going to be 1.3, giving it to two significant figures there. Okay, so that's our series example. Let's have a look at a parallel one as well. And so a number of people got this one wrong because they didn't use their parallel resistance combination rule. So the first important thing is to remember what that is. So to get 1 over the total resistance, we need to do sum of the reciprocals of stuff. So that's going to be 1 over 10 plus 1 over 5. So I'm going to write them both over 10. So that gives you 3 over 10. We've calculated what 1 over RT is. So that means that the total resistance is actually going to be 10 over 3, which is just 3.333 blah, 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 blah ohms. We want the answer to two significant figures, so I'm just going to write 3.3 in there. And we want the cell current, so we're just going to use the equation we used before. Remember, we used I equals V over R. Our potential difference is 4 across the whole circuit. The total resistance we've just calculated is 3.33. So let's just stick this on my calculator. 4 divided by answer gives us 1.2 amps. That is already a two significant figure number, so we don't need to do anything to that. In this case, the voltmeters will both read 4 volts, and it wants it to one significant figure, so we wouldn't be writing like 4.0 in there. And we know that because they're in parallel, so the potential difference across them must be the same. And we know that like V1, so if we draw our loop like we did earlier, we know that the potential differences in this loop must be equal to the EMF of a power source, so V1 must be equal to 4 volts, and therefore V2 must also be 4 volts because they have to be the same as each other. So which means current A2. So again, if we want current, we're just going to use V over R. So the potential difference across that section, remember, is 4. The resistance of the section containing A2, you can see, is 10. So I'm going to write that as 0.40. Why did I do that? Because it told us it wanted a 2-digit figure number. So let's do 0.40. Okay, and we want the current through A3. So A3 is going to be A1 minus A2. So we're just going to do 1.2 minus 0.4 gives you 0.8. It wants it to 2-digit figures, so I'm going to write that as 0.80 in there. And does that make sense? Yes, it does, because we'd expect A3 to be bigger than A2, and we'd actually expect A3 to be double A2 because it's going through half the resistance. So that makes sense, and all of our current rules are obeyed, so that looks good. Okay, so let's look at our last circuit, which I broke down into 2 questions, but we've got a combination of parallel and series. So potential difference laws this circuit must follow. So there are a few options for this. So let's actually scroll to that question and see what the options were. So we want the potential difference ones. So the options are we could have V2 equals V3, V1 plus V2 plus V3 equals 4, V1 plus V2 is equal to 4, or just V3 is equal to 4. Okay, so first thing is that V2 and V3 are in parallel with one another, so they must be equal to each other. Okay, so we can say that straight away. So V2 must be equal to V3 because they're in parallel. They always have to be the same, no exceptions. The other thing we can do, other law we can come up with, I'm going to draw some loops around the circuit. So a possible path for current in this circuit would be to go around here. So we know that the EMF, total EMF is equal to 4. So we know that we can essentially say 4 must be equal to. And through this loop, we had V1, we went through V3, and that's it. Let's draw the other possible path current could take. So it could go through here, go around the bottom, and it could go around here. And so in this circuit, we would say that 4 would be equal to V1 plus V2. So these are the 2 possibilities we could have for the other law. So let's see which one we need to pick. Oh, we could see here we've got V1 plus V2 is 4, which matches up with this second one that we drew. So we're going to pick that one. Okay, and we could have put those either order, it doesn't matter. Okay, current laws that the circuit must follow. So first suggestion is all the currents would be the same. That doesn't make any sense because A1 is going to split up between A2 and A3, so not an issue. It says A1 could be equal to A2 plus A3. That looks good. And I think that makes sense in our circuit. So A1 is equal to A2 plus A3. Okay, there we go. So that would be the law there. Just a quick thing, I keep using the symbol A. Remember, the actual symbol for current is an I, but I'm using A to stand for ammeter reading 1 or ammeter reading 2, ammeter reading 3. That's why I'm using an A, but strictly speaking, I probably should be using an I because that's the symbol for current. Okay, so those are our general rules. Let's now do some specific calculations with this one. So, the first thing we want to calculate is the resistance of the parallel resistors. So remember that when we have parallel resistors, it follows this rule here. So in this case, the 2 parallel resistors are both 10. So this is nice and easy. It comes out as 2 over 10 or just 1 over 5. And that means that the resistance of the parallel sections is 5 ohms, and it wanted it to 1-to-the figure, so I can just write a 5, not 5.0 in there. And therefore, the total resistance of the circuit is going to be 10, because if the resistance of this whole section here is 5, if we add that onto this section over here, which it's in series with, we'd get that it's 10, and that's 2-to-the figure, so that's absolutely fine. This means that the current through the cell is, so we're trying to calculate what A1 is, so the current is going to be the potential difference divided by resistance. The potential difference we've applied across the whole circuit is 4. The resistance of the whole circuit is 10. That's going to be 0.4, and I want it to 2 significant figures, so it's going to be 0.40 amps in there. Okay, we can then calculate V1. So that's what we'll do next. So remember, V1 is going to be the current going through that resistor times that resistance. So we know the current going through this 5 ohm resistor is 0.4 because the current isn't going to have changed since the ammeter. We know the resistance here is 5. So this is 2.0 if we're giving it to 2 significant figures there. And therefore, V2 and V3, well, if you remember, so remember the laws that we applied earlier. So we said that V1 plus V3 must be equal to 4. So therefore, V3 must be equal to 4 minus 2. And I'm going to give it as 2.0 because we want it to 2 significant figures in there. Okay, and we'd find the same thing for V2 as well. We'd find that was 2 volts as well. So once we know V2 and V3, we can calculate A2 and A3. So let's do that. So if we want A2, it's going to be V3 over, and we know that V3 is 2 because we just calculated it. We know that the resistance it's passed across that section is 10. And so we know this is going to be 0.2. It wants it to 2 significant figures, so 0.20 amps. And we can do the same thing for A3. So that's going to be V2. I probably should have labeled my potential differences more logically, but never mind. And again, the potential difference we know is 2. The resistance across in this loop here, we can see it's 10. And it comes out as 0.20 amps again to 2 significant figures. Do those values make sense? Well, yes, they do, because 0.2 plus 0.2 gives you 0.4. So our current law has been followed, and those resistances are the same, so we'd expect the current to be the same. So that makes complete sense there. So that's our last question, looking at incorporating our resistance laws in amongst our current and potential difference laws. And it is critical that you know each of these laws and you've got them clear in your head, so that we're not with parallel resistors just adding them together or something, which quite a few of you were doing.